Good evening, everyone. The talk today, Professor Henrique de Andrade Gomes. He is a junior research fellow in philosophy of physics at the Oriel College, University of Oxford. And the title is Timeless Words.
Thank you. Thank you. Thanks, Nadia, for inviting me and taking care of everything. It was great. I've really enjoyed the conversation so far and the conference as a whole. It's not very often that we get to focus on this topic. I think it's very important conceptually and technically, but also daunting. So when I was preparing for this talk, I kind of had a different picture in mind of what I was going to present. It was going to be something more related to quantum mechanics. But I realized after Julian Barber's talk, etc., that it would be necessary to try to give you an introduction that differs slightly from the abstract that I provided. So please don't get too attached to the abstract, because it's not going to be at least about the first half of the talk. Then if I have time, I'm going to tell you a little bit more about how I think of these, how to think about probabilities in a timeless context at the end. But all right, let's get straight to it. First, I'm going to tell you a little bit about some of the problems and how they arise, the problems that at least pushed me to think about time and timelessness in physics. So as we all have grown accustomed to thinking of gravity, it is about the geometry of space-time, right? We think about space and time being curved, and usually, in fact, the important components of curvature that we see, for example, in the solar systems are time components. It's the time that gets curved more than space in the rest frame of the Earth. And general relativity is usually sold to us as this kind of block. And, Minkowski has this famous quote, whereas from now on, time and space become part of a single entity. But there still seems to be a difference between spatial intervals and time intervals. We are used to it. Even in GR, there seems to be some remnant of that. Because duration, even in GR, involves dynamics, right? We, as Nadia and other people have said, duration somehow has to involve change. At least that's how we think of duration and time. It involves change. We're not used to thinking of time kinematically, for example, in the sense of space-time, but even in space-time where nothing happens, time still ticks. And whereas for space, spatial intervals are non-dynamical. And the way you can talk about that is that you can think about its distinction between dynamic and non-dynamical more operationally, is that, or you could also think about it in terms of the equations of motion, elliptic and hyperbolic, but let me not be technical for now. We can set up a system spatially, if X is a spatial point. We can set up the state of a system at X, and independently, we can set up the state of that system at X plus delta X, or largely independent. There are some constraints, which we'll get to. But for time, it's different, right? For time, it seems that once you set it up at T, you're kind of condemned, at least up to diffeomorphism invariance, you're condemned to what it's going to be its state at X plus delta X. You don't have any freedom anymore, because that state involves now dynamics. It's the laws of the theory that are going to determine how the state is at X plus delta, at T plus delta T. And so there seems to be this big difference that doesn't quite fit these aphorisms of Minkowski and other ideas that we're used to thinking about in space-time. So here's one picture that people often put up about general relativity and the block time kind of view, the block universe. So here in the block universe, you think of this as a kind of a frozen block of ice, so people say it's everything is there, right? It's kind of misleading to say static, because static already invokes some notion of time. It's just that it's all there. All moments exist on the same status, on the same level. There's no notion of flow as you going from one state to the other. And there is a very different contrasting view, the presentist view, where only the present is the seat of reality. Right? This is one picture where the difference between time and space is very prominent, because here you actually do have something that is the instantaneous state, and time is what pushes it forward moment by moment. Right. And so this is the main difference between the two. And I got interested in this problem of time in gravity when I started thinking about quantum gravity. And this has been an open problem for 80 years. And obviously, people have suspected time, as I would say, there are different notions of time in gravity and quantum mechanics. They have suspected that time is the culprit for this distinction, this obstacle for quantizing gravity for a while now. So what is the main difference now? It's not exactly the presentist, but it's more similar in the quantum mechanical sense. Time is more similar to the presentist time. So in GR, as this picture I think has already been presented here, for the three types of times and their melted clocks. In GR, time is fluid, it's more arbitrary. In QM, it's quite rigid. In standard quantum mechanics, it's quite rigid. Even if you talk about QFT, it's much more rigid. It's only in Minkowski space-time, and it has a very rigid asymptotic structure. But without a fixed definition of time, when you're thinking about quantum mechanics and you take into GR's absence of this fixed notion of time, and this a priori distinction between past and future, or no a priori distinction between past and future, how is it that you're going to interpret conserved probabilities in quantum mechanics, right? Conserved probabilities are conserved in time. Usually there is this background of time that is picking forward, and we think that probabilities are conserved from instant to instant. But if this time is not present of the general relativistic structure, how are we going to reinterpret these things in quantum mechanics? So I'll briefly mention another issue that is much more the focus of research in quantum gravity than time, which is this idea, sometimes called the non-perturbative renormalizability of GR, which is that the point here is that when you're trying to treat general relativity perturbatively in quantum field theory, the space-time fluctuations themselves source gravity. That's because it's a non-abelian theory, so it's the same thing with QCD. But here, they source it much more strongly because they have inappropriate, I would say appropriate, but inappropriate mass dimensions. And so they source it much more strongly. And this creates a runaway effect if you're going to try to treat it perturbatively. And perturbation theory fails, essentially. Right. Now, okay, so what do physicists want from quantum gravity? This is an aside to say, look, this is what most physicists think when they're talking about the problem of quantum gravity. And most physicists will say, well, I want a theory that has quantum field theory and GR, and includes effects with the Planck constant and the gravitational constant and light. So if you include all these, there are effects that include all these constants, then we are talking about a quantum gravitational effect. But this is too weak. We have effective field theory, excuse me, that you can treat, in the modern way of thinking about QFT, in the Wilsonian way of thinking about QFT and effective field theory, you don't care so much about non-renormalizability. You just say, look, yes, things blow up at a certain energy, but I'm just going to put a black box on that. I don't care what happens at such high energies. I'm going to rely on the theory at lower energies. And at lower energies, you can get a gravitational potential that includes all these effects by looking at one loop amplitudes and things like that, and perturbations around Minkowski background. Another thing that people might ask for is a perturbatively renormalizable gravitational action. So this is even more than this you get just from GR. but you won't say, well, I want something, a different kind of theory that is it's renormalizable, right? This is not renormalizable, but now I want a renormalizable theory. But we have also theories about gravitational theories that are renormalizable around a classical background. So Rojava-Lifshitz is perturbatively UV finite, via gravity as well, and so on. Should it also resolve singularities? You have all kinds of questions that you could ask. Have only spin two gravitons, conserve probabilities, and then some of these other alternates fail at some point, and not others. I'm not going to obviously attempt to solve all these issues here. I'm looking at a very narrow domain of problems with quantum gravity. I'm not thinking about all these issues. So for that, I think it's useful to distinguish between two kinds of problems, like in the studies of consciousness. And I'll call the previous technical problems easy. Of course, they might be the hardest, but I think they're kind of a different quality of problems, a different type of problem. So these technical problems, normalizability, for example, I'm calling it easy. And so what are the hard problems? I think the hard problems is reconciling the foundations of a quantized theory of geometry. So why do I think that these foundations are not really, they don't have a happy marriage, so to speak? So first of all, I think you can think of quantum mechanics as at least telling us about how a state evolves deterministically in some time. It could be a clock time, but we'll get to that. And it goes to psi, goes to psi t. Does this have a laser now, right? It's fine. And it should give, furthermore, it should give this idea of conserved probabilities that moreover tell you what kind of frequencies you are most likely to witness in experiments. Now, general relativity, on the other hand, tells us which space-time geometries are compatible with which distributions of energy and momentum, right? I prefer this phrasing of it than saying something like tells matter how to curve and space-time, tells space-time how to curve and matter how to move. Because this is less causal, it's just giving the space-time as a whole, and there's a distribution of matter that's compatible with a certain distribution of space-time. Right, and so I'm going to give you the 1-star and the 2-star problems. It's not I'm not saying which one is harder, it's just an enumeration. So you have the quantum, I'm gonna give you two quantum mechanical properties that I've taken as fundamental. One is the quantum superposition principle, and the other is that there's an evolution in time of observables that are also local in time. And these clash with, so the 1-star clashes with the 1-star, and the 2-star clashes with the 2-star. The 1-star class, so the quantum superposition principle clashes with the fixed space-time causal structure, as you see, and the evolution in time of observables local in time clash with gravitational observables that are usually non-local in time. So you obtain, well-known observables in GR, like the integral of the Ricci scalar over the whole space-time, supposing that doesn't diverge. That's a gravitational observable, but it's very non-local because you're integrating over all space-time. So here's an example of this clash with superposition versus causal structure. Bill Unruh touched on this briefly. If you have matter sourcing gravity through Timmy nu, but of course, you're going to have superposition of matter, and matter, since it back reacts in gravity, you should think of a superposition of causal cones as well, right? Because the geometry is defining for you what the causal cones are. But what does that mean? What does a quantum superposition of the metrics mean? How do we think of superposition of causality? It's a very tricky thought to hold in your head. So for relativistic quantum field theory axioms, you can also see this. Usually say that for operators that are space-like separated, the commutator vanishes. But then the definition of space-like depends on the metric, right? So you can't really use this idea to talk about gravity, because you're presuming the value of the field that you wanted to contain in these operators or fluctuate and so on. So it's kind of a circular argument. Right, and this mismatch, as we'll see now, between the general relativistic covariance, so to speak, and the time evolution of quantum mechanics, it shows up in all kinds of quantum gravity theories. It definitely shows up in loop quantum gravity. There are different issues related to the Hamiltonian. It shows up in some preferred spoliation theories like causal dynamical triangulation from Java, ADS-CFT. There is this problem with bulk locality. How do you recover bulk locality from holography? There are all these kinds of issues. So, I don't believe this, by the way. I don't believe the fundamental GR notion of time is dead, but let's hold that question in our head and think that perhaps, this idea of general relativistic time is something that should be only recovered effectively. By effectively, I mean it's not fundamentally there, but maybe through the dynamics, maybe as an approximation, we recover it. And there are loads of approaches to quantum gravity that take this view. So let's make an analogy now. Suppose that you were in the 19th century and you were just before creating quantum mechanics. You don't really know yet what quantum mechanics is. And then someone comes from the future and tells you determinism is dead. And you really believe them. They show their credentials, and you're okay. All right, I believe determinism is dead. So how do we proceed with our theory? Well, one thing we could do is to look for a formalism that's not explicitly deterministic, that doesn't, contain determinism in its inception, in its very definition, but that somehow coincides with Newtonian dynamics, right? Newtonian dynamics is deterministic. It has its forces, and you just calculate the second derivative and so on. And here's, you had that already in the 19th century. You had Hamilton's least action principle, where it's not explicitly deterministic. You have all these paths trying out different, being tried out between an initial and a final point. And if you had some other ideas about Fermat's principle and Henrique's Fresnel principle, you could have perhaps come up with the Feynman path integral. And it's kind of pictorially clear how the Feynman path integral recovers Newtonian trajectories, but it's not explicitly deterministic. And then you could have, and then then the game starts. You could have gone from there. So now let's suppose the doc comes and says, Marty, general relativistic time is dead. So suppose we believe him and we want to do something similar. Now we also want to think about a theory that gives the same results as GR, but perhaps has a slightly different notion of time. So general covariance is not part of the foundations of the theory, but you want the theory to recover. Now, just like in the 19th century physics, you might have appealed to this Hamiltonian principle of least action. Here, you could also think about a Hamiltonian framework, because although there's this equivalence, the Hamiltonian framework, it's not in the foundations of the Hamiltonian framework that is generally covariant. Right? The Hamiltonian framework is a 3+1 formulation. It takes time and space to be radically different. And now you use phase space, you use a configuration. The configuration here is the metric of the universe at any instant, and the momenta is associated to a change of this metric. It's a little bit subtle how this happens in association, but anyways, you can just think of it as another field, as the momentum of the spatial metric as the momentum. And then you get to geometric dynamics. And we've talked, I've noticed that in several talks we mentioned geometric dynamics. People mention lapse and shift, but I'm not going to go through it in detail. But for those of you who are a bit lost, the idea is that you foliate space-time like that with some leaves, and then you have coordinate grids that connect the leaves, and you have the normal to the leaves, and the lapse and shift, they tell you how these coordinate grids that connect the different leaves are related to the normal. So it might displace, it might it might lengthen the normal, and that's encoded in the lapse, and it might shift the normal, or maybe shift it relative to the normal, that's encoded in the shift. So here you would rewrite the metric in terms of this kind of adapted coordinate system to this to these coordinate systems that I described, to leaves. So here you foliate, you get a different formulation of the Einstein-Hilbert action with the metric and the time derivative, lapse, etc. You do a general transformation and you get to the Einstein-Hilbert action, now written in terms of the metric, spatial metric and its conjugate momenta, and two auxiliary variables or Lagrange variables, the lapse and the shift. Now, you also find that there are functions when you do this. I'm not going to go into this in detail, but you find that the transformation is not invertible between the momenta, the metric, so metric momenta doublet to the metric and velocity doublet is not invertible. You get constraints. You get constraints on the that you express in terms of your momentum. Now, usually these constraints, they are related to some quantity that's conserved, right? So you can write conservation of angular momentum in terms of the constraint. And there's also this association between conservation laws and symmetries. So conservation of angular momentum is associated to symmetry under rotations, conservation of linear momentum associated to symmetry under translation, etc. Here it's a bit different. Here, what you get in GR, you get some local constraints. So not exactly conservation laws like this, but constraints on your equations of motion or your laws. And I'm not going to go through it once again, but what you get for these constraints when you do the Lagrange transformation are two types of constraints. One is called the diffeomorph, three-dimensional diffeomorphism constraint. This is the covariant derivative, it's covariant divergence of the gravitational momenta. And this is a more complicated quadratic constraint, but depends quadratically on the momentum. Now, so let's first look at the momentum constraint. The momentum constraint, it's kind of trivial to see that it generates, so just like you think of angular momentum as related to rotations, as generating rotations. Here you can think of the spatial diffeomorphism or the momentum constraint as generating three spatial diffeomorphisms. So the way you see this is when you talk about what generation means, this talk, symplectic geometry or Poisson geometry, you calculate essentially Poisson brackets between this constraint and general functions of the metric and the momentum. And what you find is that any general function just gets transformed, whatever is dependence on the metric and the momentum, where now it's that same dependence, but for a shifted metric and a shifted momentum, shifted by this diffeomorphism. Now, this is a very clear geometric meaning. What is it that this constraint generates? It just generates spatial diffeomorphisms, generates spatial transformations, like the angular momentum generates angular transformations. This generates general reshufflings of your spatial points. The quotients by this action, so if you want to extract what is it, the physical information that is preserved by this symmetry, it's kind of clear. It acts on each spatial surface. And if you have anything that depends only on the geometry and not on the metric, let's say not on the coordinates, then that will be preserved by this constraint as well. So you ask what is this constraint enforcing? It's kind of enforcing a spatial relationism, if you will. It's enforcing the idea that your theory should only talk about things that do not depend on spatial coordinates. And it's a very simple kind of symmetry and constraint. It forms a nice Lie algebra that, as you would expect, where you get the Lie bracket between the generators, the spatial. This U and V are spatial vector fields, and so on. And the constraints are linear in the momenta, canonical quantization, symplectic reduction. All of these things are relatively unproblematic. Okay, this is has a momentum map and so on. I'm definitely not going to get into that. And as I said, when you want to try to implement this, when you do this, this very facile way of quantization where you only put hats on operators. If you want to quantize the wave function, all it says is that the wave function depends only on the geometry for which I put square brackets on. So it depends only on the superspace of spatial geometry. Alexander had a nice figure from Wheeler about what that superspace was. It's a infinite dimensional space where each point is a full three-dimensional geometry. Okay, so now what about the Hamiltonian constraint? Now things are much more delicate. It's not straightforward. Usually people say that it generates time refoliations, just like the first one generated spatial diffeomorphisms. This one will generate time refoliations. You started out with the foliated space-time. Now the idea is that the Hamiltonian constraint can change. But there are complications here that, first of all, in the Hamiltonian formalism, there is no space-time. So, in principle, you shouldn't be talking about refoliations. So in order to talk about refoliations, you need to translate it back to space-time. And then you find that this generates time refoliations only on shell of the Einstein equations, or at least on shell of some of the Einstein equations. So it's true that for the space of solutions of the Einstein equations, the action of the Hamiltonian constraint can be pulled back with the Legendre map to generate space-time diffeomorphisms that are normal to the surface, to a given spatial hypersurface. Now, even then, it's not very clear what it is that this will preserve. It's not. It has a little bit of a delay. Sorry. Well, anyways, in contrast to the action of the diffeomorphisms, you can't really pinpoint now what are the invariant degrees of freedom. Right? We say, oh, things that are time independent, but here you have this, what some people call multi-finger time. You don't have a single time evolution. What is it that you get that is preserved by this constraint? It's not as clear. There are also other problems. These don't really show up in cosmological models, but in full GR, you don't really get a set of algebra. You don't get an algebra of constraints, so to speak, because of the presence of this G here. It involves the metric. So it depends on the phase space point at which you are. The algebra itself, the algebra of constraints, depends on where you are on phase space. And this is actually quite annoying to deal with when you're trying to quantize. And many people have mentioned it already. This gives rise, when you try to quantize it, gives rise to Wheeler-DeWitt equation, which is a Schrodinger equation for the zero energy eigenstate. So timeless. Right. I hope that maybe I should have given this as the first talk. So that people would know what timeless we were talking about. So, so here's a summary. We have two kind of constraints for GR. The supermomentum constraint related to spatial diffeomorphism, this shuffles spatial points around, and the super Hamiltonian constraint, which is the related transformation of space-time, is an on-shell time refoliation. It might shift the definition of time at each point in space. And the dynamics are here because the Hamiltonian is it's a combination of constraints. So the Hamiltonian itself, the generator of evolution, vanishes on shell, which means that the dynamics themselves are generated by symmetries, which is a funny thing. Okay, so now we move one step forward, right? We started off by saying, okay, let's first put GR in this formalism where covariance doesn't come in at the ground level. Now let's see if we can identify another kind of theory that doesn't even have this recovery of covariance first, and then we're going to work with this theory to then try to recover covariance again later effectively, but for a different theory where covariance is really not there. Here, covariance is still there, hidden in these constraints. So for that, I want to argue that there is a kind of a preferred notion of time for GR as a whole. Something that Julian mentioned. It's called maximal slicing and constant mean curvature. It depends, but they're very, very, very similar, these two. And if you look at numerical GR, initial value problems in GR, this is still the only way to kind of generically find out the space of solutions for the initial value problem in GR. It's used in numerical GR for many, many things. It's used partly in numerical black hole mergers, etc. It was used in the proof of the positivity of the gravitational mass by Shen and Yao. It has a nice singularity avoidance property of the foliation, which is this Marsden-Tipler conjecture, which I think has been proven now, that the CMC foliation does fill out at least the exterior of the event horizon of the singularity, if a spacetime has a singularity. And the foliation fills out the entire spacetime if the spacetime is geodesically complete. Here, singularity is being defined technically as geodesic incompleteness of causal curves. Right, so now I'm going to say, look, we have some indications that perhaps the GR has a preference for a particular notion of time. What can we do with that? And I think shape dynamics, which Julian mentioned, is a theory that runs with this idea. It just takes this idea of a preferred notion of time and gives its due. So what shape dynamics does is explore the duality of what's called the CMC constraint. So here, this pi that I wrote there is a trace of the gravitational momentum. And what is very interesting about this is that it has two different roles. First of all, if you think of it as a generator of a transformation, of a kind of transformation in symplectic space, it generates conformal transformations. Right here, I'm smearing trace of pi. You guys know this nomenclature by some scale factor, and it just, when you calculate what it does with the canonical variables, it just scales them. And it also is the gauge fixing required for the York mechanism. Now, what is this? How can we use this then? So here's a picture where you have constrained surfaces on phase space. I'm thinking of this constrained surface here as the constrained surface of GR, of the Hamiltonian constraint. And you have a different constraint surface for the momentum constraint, trace pi equals constant, let's say, or trace pi equals 0 if you're looking at maximal slices. And they intersect. They intersect a certain kind of solution of GR in the CMC gauge. So solutions of GR that admit a CMC gauge everywhere will be contained along this intersection. Now, the idea is that the main idea of shape dynamics is that you can actually construct a theory that lives in this space here. So quantizations will be different. The basic degrees of freedom will be different because this only intersects the surface in some region. It doesn't, it's not a global gauge fixing. It's a different kind of theory. It's a different kind of ontology. But you can engineer the Hamiltonian of this theory so that along this line, it reproduces GR. It reproduces the solutions that you would get from the ADM action. But it will have a clear ontology in the sense of the physical degrees of freedom will be just conformal 3 geometries. You won't have time refoliations anymore. So here's the main message, is that there exists a very special system which is dynamically equivalent to ADM in a certain region of ADM phase space, and which decouples the dynamics of the pure spatial scale degrees of freedom from the scale independent ones. And the region is that of constant mean curvature foliable Einstein spacetimes. So now I'm saying that if you take this opposite view, now the system is one that doesn't possess explicit refoliation symmetry. It possesses only local 3-dimensional scale invariance. All the constraints that you have for the theory that the symmetry generating constraints are linear in the momentum, and you're happy. The individual set of constraints form subalgebras, easy to quotient. The physical degrees of freedom are quite clear. Here's here's a figure. Here's GR. So here's the intersection of the two theories in the CMC slicing. This is the atlas as GR sees it, let's say. And in GR, you could refoliate it. You could choose different surfaces of simultaneity, and you'd get different representations of the space. But this is also a representation of you can represent this in a different gauge in shape dynamics where you rescale conformal factor differently. There's different things, but the dynamics are engineered such that they're kind of indistinguishable. These two theories for these kinds of spacetimes, not for all spacetimes, but for some spacetimes, these two are indistinguishable. Now, the fundamental symmetry principle is that size is relative and the spatial location is relative. And here you have a notion of evolution in absolute time. And duration itself, you should only, even though you have this notion, you need to infer duration as the amount of change in the local physical relation of degrees of freedom, because there is no longer this kinematical background space-time. You only have change. You only have changing conformal geometries. Okay, so you put them side by side. The local symmetry of three diffeomorphisms in evolution on shell, refoliation, shape dynamics. You have three diffeomorphisms and 3D biotransformations. By the way, I'm hiding a little bit the ugly parts of shape dynamics because I'm giving a talk to convince you that it's the ugly part is that it's Hamiltonian. Well, there have been some recent advancements which I have not participated in by Tim Kozlowski that he said, so this might be outdated what I'm saying, but the Hamiltonian that you get for this matching is kind of global Hamiltonian in space, so it's not not easy to work with, and in practice it's right. And so I'm going to skip this a little bit in the interest of time, just to say that if you what you might want to do is to explicitly probe differences between shape dynamics and GR. For that, you would focus the situations on which the CMC foliation breaks down and where it breaks down, and then you would look at a theory of shape dynamics up to that point. And it has a unique continuation, usually in terms of the conformal invariant degrees of freedom, and that continuation doesn't match the continuation that you would get from space-time. But it's very hard to do this. It's very hard to find this. And as far as I know, there's like two examples. Right. So, the examples that we tried to do is sensor black hole singularities. You patch together solely solutions of GR which admit CMC foliations, and you do the same thing with shell collapse, thin shell collapse, and closed manifolds. And there's also some interesting work of continuation through the Big Bang singularity of only the conformal degrees of freedom. And this showed that the shape degrees of freedom can be continued uniquely through a singularity. And you can use this for all the spacetimes that conform to the DKL conjecture. Right. So here's the conclusion. So I wanted to, maybe I've raced a bit too much in this last part. How long do I have? Because I was planning for this to be a first part. 30 minutes. 30, good. So the first part is, I want to conclude that we started off with some problems, that there were some issues with the standing of time in GR, that time intervals are kinematical or geometrical and not dynamical, not given by change, or at least there seem to be two kinds of notions there, and they get conflated, they get run together. In GR, symmetry is mixed with evolution and observables are smeared in time. This is the notion of block universe, and these clash with some shared notions of quantum mechanics. And in shape dynamics, in GR, one postulates a four-dimensional space-time and look for solutions which represent four-dimensional manifolds. In shape dynamics, one postulates a one parameter, smooth family of conformal three geometries evolving in time. This is very clear geometric observables. And in fact, one can show, I haven't done that here, but I could show you that it's kind of singled out. If you're thinking about just metric degrees of freedom, spatial metric degrees of freedom, conformal superspace is the most general space of instantaneous observables for the metric. What I mean by that is that the only two linear, well, that once you assume spatial diffeomorphisms are a kind of symmetry, the only kind of symmetry that is independent from this and compatible with this act that could exist acting on those instantaneous states of affairs is conformal symmetry. So you have for general metrics, if you don't want it to be something with attached to particular metrics and momenta, the conformal symmetry of the spatial metric is the only other symmetry that you can have apart from the spatial diffeomorphism symmetry. So there are some kind of nice general results, and Mercati and Anderson have also some very interesting uniqueness theorems. I have some uniqueness theorems too about how shape dynamics is kind of the only theory that you could get given some consistency. So I'll just tell you what Mercati and Anderson's results were because they're simpler. If you start from a kind of action that's kind of PSW action, it's a kind of way of representing an action for space-time, and you can start with very general kinds of Lagrangians, but then you try to make that will generate constraints because it has a local square root. Anyways, I'm not going to get too much into that, but the constraints, you run this direct algorithm machine to tell you when the constraints are compatible, and for a very, very, very large class of actions, you get only two possibilities, either GR or shape dynamics. So there are some interesting uniqueness and results for getting to shape dynamics, and it's interesting that it kind of disentangles evolution from symmetric principles, and this is kind of a thorn in our neck. And it will match general relativity in many circumstances. Essentially, whenever it's possible to synchronize clocks so that the Hubble expansion is spatially constant. You can do that throughout the space-time, then there is no distinction. Then you can recover that solution from the shape dynamics side. So here it seems if we're going to take this, Doc's advice literally, maybe we have succeeded, right? Maybe we have found a theory that doesn't embody this notion of covariant time from the beginning, but recovers it dynamically, recovers it for a subset of solutions and includes dynamical principles. But it's not there as kinematically or geometrically or without dynamics. Okay. So now let me. Can't see what I'm doing. Sorry, I thought this would have done over smoother. Yeah. That will give you a chance to. How do I put full screen on PowerPoint? Wait, how do I hide this? He's not here. No, sorry. I just wanted to hide this so I can put it on full screen. I can see it here. Sorry. Cool. Right, so I still have 30 minutes, you said, right? Okay, so I'm not going to give this whole talk, but I want to say now, I think if you take this approach, there are a bunch of problems that might get resolved from the perspective of will-o'-the-wisp quantization and so on. So as has been said many times before in this conference, when we quantize the will-o'-the-wisp equation, you can try a kind of a WKB approximation for the wave function, where here, so here you would think that, sorry, I don't know if you can see this. Here I'm thinking of this as an action going, the wave function is given by the phase. Well, there's sorry, not this. It's wrong. Okay, wait. Right. So you have gamma. Where here gamma is our paths going. There are certain kind of space-times that you can restrict in different ways. You can restrict them either via a kind of boundary condition, like the tunneling condition, which I think Natalia has talked about, or you can restrict them by using complex metrics and requiring your spacetime to have a single boundary. Right. And the idea here is that if you do this kind of approximation and you expand, and there are different kinds of expansions, you can expand it in terms of you use the Hamiltonian constraint here for at least for mini superspace. For mini superspace, you don't see a lot of the problems that I was talking about. You get at each order of the expansion of this equation, you get its own equation in order of Planck mass or different parameters. And you get, for the first order, something like that the space-time needs to be on shell or needs to satisfy the Hamilton-Jacobi equation for GR. And for the second order, you satisfy some Schrodinger equation in terms of background time and so on. And you also get, sorry, you get something like this. You also get, or maybe here I should put A somewhere else. So here's the idea. You have some paths. Let's suppose for simplicity that we're using kind of a fixed boundary condition, and which is just a particular point in configuration space. And to find out what psi of G for a certain G here is, I just do a path integral over all the paths that arrive here. And now, if there is a single, let's suppose if there is a classical path here, something that extremizes the action, and let's say this is S naught, so there's a gamma naught, which is extremizes the action between this point and G, then I'll write this equation down more properly afterwards. Then this phase, the sum over histories for all these paths here, it gets approximated by a single phase. It gets so that so psi of G becomes approximately just e to the is of s naught of gamma naught. There's some constant here, and then you can get further orders, right? But it can't be too close here. So right, so this has to be the on-shell action has to be much greater than h bar, and so on. So if you get too close here, you can't use this. If you get too close to this origin here, to this boundary where I've set the boundary condition as a delta function on this configuration here, let's call it star. If you get too close, the approximation is no longer valid. Okay, because too close in Hamilton-Jacobi length. Right, and then what you find, what is also interesting, is that in this approximation, you can actually think of this A as a kind of a probability because it will be conserved for any other point that I find along this classical trajectory. For this notion of background time along this trajectory, the norm of k squared is conserved. So you can think of this kind of. So you can think of probabilities along these semi-classical paths as being conserved. And then, you kind of recover a Born rule in a certain way, which I'm not going to go through here in detail. And you can ask Leonardo about that as well. And I'm sure he knows it much better than I do. And one of the issues that you have here is that you get this Born rule probability, but only for these kinds of paths, these kinds of points, for points that are very far away, for which there are no competing histories. Sometimes this is also called the coherent histories approach or probabilities. So if you have these paths that are very far away, for which there's a single history for each, and there's a sense in which you can recover Born probabilities for these decoherent histories because they don't interfere anymore. And here, one of the things that I wanted to do or talk about is, first of all, get rid of this assumption that you need to define probability only for these histories that have decohered. So I would like to define probabilities for histories that are along that might get some interference. And I also wanted it not to be at least foundationally to be applicable also to general gravity, right? So here, this picture here only works in superspace because this picture here only works in mini superspace. Mini superspace is the restriction of quantum gravity to cosmology, where you have very few degrees of freedom. If you were not in superspace, there isn't a single classical path ever from one point to another. You can refoliate and get all kinds of different paths, and it's very hard to deal with that. So what I think shape dynamics gives you is a mechanism or a tool to kind of apply the same methods as are used in quantum cosmology more broadly, because they're just not applicable, even conceptually. Let's not even get into the detail about calculations. So the thing that I worked on a little bit is to using something like shape dynamics. Think about configuration space of the theory, conformal superspace, and you just define a probability density there given by the wave function. And that won't care whether histories are decohering or not. It will just give you a probability wave function for that, probability density for that. I'm going to talk about this a little bit. So probability comes in at the ground level, so to speak, and is defined wherever, and it coincides with something you would like from this kind of decoherent approach that is applicable to mini superspace when you have very few degrees of freedom. And I think this has, so a parallel talk could have been given, which I'm trying to fit the two into one. I'm not going to succeed, but I'm going to give you an inkling, in which you actually get a different interpretation of quantum mechanics, a slightly different interpretation of quantum mechanics. So usually quantum mechanics also has its own intrinsic, forget about quantum gravity. Quantum mechanics has its own conceptual obstacles, right? The measurement problem. And this is usually, as described in that nice graph from Penrose that Alex put up, this is usually described as a clash between the unitary evolution of the wave function and the non-unitary collapse of the wave function. And many worlds resolve this by denying the non-unitary collapse of the wave function. It just says the wave function never collapses. It's just different branches stop interfering, and you're on a single branch, and that's it. And there's this common assumption in foundations of quantum mechanics that you first understand the theory in simple non-relativistic particle setting, like in many worlds, and then you voice that interpretation to more advanced theories. Here, I want to say something different. I want to say, look, many worlds has difficulties with space-time. It relies on normal notions of time and so on. And you can't generalize it. Where in many instances, this other idea that there's just a probability density over the configuration space of your theory, it also resolves this paradox because it denies there's a unitary evolution. Everything is already collapsed, so to speak. And it is generalizable to quantum gravity or to the space-time context in a way in which I don't know if many worlds is. Okay, so I'm gonna blaze past this. Here's the Harker-Hawking wave function, which is a particular realization of this idea here, where here you have a wave function is defined here. I also included some matter content, and defined as this path integral with one boundary kind of fixed, or non-dynamical, let's say, or not a variable. At least we only have one variable for a boundary state. Here it's confusing because I'm switching nomenclature from for spatial metrics from G to H. So sorry. Okay, so what I want to say is that there's a kind of a primitive notion of probability. Maybe I should call this pre-probability. It's not really a probability yet, but there's just this idea that you can compare the masses of two regions in configuration space, right? So you have a region A and a region B. It's some region in configuration space, and it has a kind of a mass function there, which is given by this psi squared, and you can just compare. Essentially, what I'm saying is that probability here is really frequentist in the sense that there are two regions in the configuration space, and one region will have more points, will have more configurations than another. So, if there's a copy of you in each one of these, there will be more copies of you here than here. So there will be more copies of you, let's say, observing a given outcome of an experiment in one region than in another. And then heuristically, you would imagine that if the two regions are the differences between two regions in the particular chord graining that you're describing the regions in is parametrized by finitely many, or even if denumerably many parameters, then you can mix, even though the individual volumes definitely need regularization, and this is a big problem. I don't know how to do that, but the quotients are already regularized because you describe the differences between the two regions in terms of finitely many parameters. Right, so the idea here is that I don't need to invoke decoherence to describe probabilities, but there's a lot of work to do. So I'm not going to go through the Everett idea of branching. I think most people are familiar with that. The idea is that you have a wave function that interacts with the system. The wave function has many degrees of freedom. You can think of psi 1, 2, 3, 4, 5, 6, 7, 8. And each one of these gets kind of entangled with the point state or the apparatus. And this psi A and psi B have many degrees of freedom. Whenever they interact with something, they detect something, they become effectively orthogonal. So the reduced density matrix becomes approximately diagonal. Right. But it has lots of questions that people struggle to answer in many worlds. It's what is sufficiently approximately orthogonal? What is the norm? A decoherence is a semi-classical approximate notion. Can we get more than one decoherence spaces, for example, for different time scales? Why can we discard recoherence, right? So usually you talk about probabilities in many worlds when you say two branches have decohered, so they're not going to interfere anymore. But who knows? They might recohere later on, and then you have effectively collapsed the wave function, and you don't know, you can't recohere them anymore. And how do we count the branches? Standardly, this is done by some strange ideas in decision theory. You count the branches in terms of betting, what you would bet would happen in the future, and given the current state of affairs. And as David Albert says, like, I want an explanation of its statistics, and I got an answer about how to make rational decisions. It just seems incongruent, right? With physics as being foundational, fundamental. You don't want to derive the Born probability as a rational outcome. And there are more questions. What is the Hilbert space in which the wave function lives, and how do we relate that to the real world? This is my colleague Chris Stimpson, former colleague David Wallace. They say they want to say, well, it's more than just a vector in a Hilbert space. You want to imbue it with more structure. And you say things like, and they say this in the paper, that the physical universe is, as we have said, very highly structured, whereas Hilbert space vectors seem pretty much alike. The problem is partially resolved when we recall that a quantum theory can only be specified if we also give some particular set of observables, e.g. the position and momentum operators in one-particle quantum mechanics, or the various field observables in QFT. This breaks the symmetry of Hilbert space, allowing us to see how merely mathematically distinct vectors could represent physically distinct states of affairs. But these are not part of the wave function in the many worlds, and they're not part of. They don't come in a natural way. They have to be stipulated. So they try to implement this in something that's called space-time state realism. Yeah.
Sorry, I don't understand the last part. Once I have the Hilbert space, I also have the observables, right? Because the observables is the set of bounded operator on the Hilbert space.
Well, the question is, you're also thinking about having been given the set of operators. So for many worlds to get going, you just need the evolution, the Hamiltonian, and the state vector. And the idea for many worlds, at least like this, maybe people call this mad dog regressionism, is that you need to somehow extract the rest of the things from that. And Tim Otten has criticized many worlds severely for that it just doesn't talk about real things, about particles and configurations and so on. And anyways,
yeah, maybe I ask you after, because it's about this quote, right? That you need to pick a particular set of observables, but if I give you the Hilbert, you also have the observables right away, right?
Well, it depends on which way you give me the Hilbert space.
L2 of R or CN or some other Hilbert space. I can then look at the set of all bounded operators on that Hilbert space.
Right.
It's defined by that Hilbert space.
Right.
And so then that's the space of observables.
Well, right, but what is the physical meaning of those? We want to talk about particles and positions and things like that. And it's unclear how to relate the set of bounded operators to these things, set of bounded operators in this abstract space to the real things that we measure. At least that's the criticism that they're trying to avoid here. And they try to do something where you already have a space-time and you associate a state rho to each region of space-time and so on. So they're trying here to make many worlds compatible with space-time physics as well, because in many worlds you have branching in time. The branching of the wave function happens through Hamiltonian evolution. But I'm not going to go through their construction, but at the end of the day, their construction to try to reconcile many worlds with space-time doesn't really work. There's a paper in 2020 by Noel Swanson that shows that you have basic problems with that, given the Richelieu theorem, and because quantum field theory usually gives you a type 3 von Neumann algebras, and these can't be neatly separated in the way that Timpson and Wallace envisioned. This is just to say, you don't need to know the details about this, just to say that many worlds kind of presumes this background time, and it's not clear how to make it compatible with a fully covariant space-time structure, okay? Right. Here, I think, but in any case, this picture also, it's this picture that I gave here of this wave function and configuration space also has its own problems. You want to try to define regions and subsystems, and all you have here is the full metric or the full configuration of the whole space. And so the regions and subsystems, they shouldn't be fundamental, but they should be extractable somehow from this wave function. I'm gonna tell you how it is. And so this condition is already enforced by this formalism because space here is fundamental. You have spatial configuration. So this this is not something you need to worry about as you do if you're just thinking about a fully covariant quantum theory. Right, and then what is the time for which probabilities are to be conserved? This is also actually something that we need to encounter here, that we need to talk about. And I'm going to try to tell you a little bit. How much longer do I have?
5 minutes.
Okay, so let me go straight. So this is an idea that motivated Julian Barber to talk about many instants. The idea is that these are photographs. And at different instants, so this is a later photograph, this is an earlier photograph, and this is an earlier photograph. And the idea is that this photograph here kind of contains a record of the configuration at an earlier time. And this photograph contains record of configuration at an earlier time. This, by the way, is the Mott bubble chamber experiment. These are ionized particles that there's a condensed gas here, and the particles kind of nucleate bubbles as they're. It's a prototype of a particle accelerator kind of experiment. But the basic idea is that you can describe this, and people have done this. This is how they describe this experiment by time-independent quantum mechanical treatment. And you take the nuclei to have fixed position in 2-state electrospheres. But you can still get you can extract some notion of time from that static picture. Because as I said, later snapshots contain records of earlier snapshots. To get a picture like that, you do need this original, an origin of this process to be a very low entropy initial configuration. Or again, it's misleading to talk about initial here, but it's a low entropy configuration where all the detector states are down. And if you're thinking about this in a configuration space, each one of these is a point, and they form a curve. And each point along the curve is a kind of, in a sense, contain records of points of the other points that came earlier in that curve. And this is the idea that I think we would like to try to emulate for this picture here, which is still very abstract, right? It's an abstract picture where I have a density on configuration space. We want to talk about records, about if you want to talk about some recovered notion of time on which probabilities to be conserved. This is going to, and time is duration. We need to have some notion of records and how probability is going to be conserved in terms of records that these configurations have. So what is important here is that these probabilities satisfy the Markov property. So the probability of getting this configuration here depends only on the probability of getting this configuration here. So it factorizes. So the probability of n, the probability of this configuration given the initial configuration is arrived at by the probability of getting this configuration from given this configuration, and then this configuration given this configuration. So it factorizes. It's something that tells you that you don't really need to know, what happened at the beginning of the universe to kind of calculate probabilities in the lab.
Are you depending on a universal probability, like a background?
Yeah, I'll get to that. So here's Julian Barber says that about the Wheeler-DeWitt equation. Once again, he has this idea, which in a different form, he called these time capsules, where later configurations had records of earlier configurations. He called it that they had time capsules of the earlier configurations. And he conjectured that the Wheeler-DeWitt equation of our universe concentrates all of its well-behaved solutions on time capsules, on configurations that have records of earlier configurations. And he conjectured that this would hold for theories of quantum gravity, so that we could extract time, even though time is not fundamental there. You just have configuration space, some static density on configuration space, but you can kind of extract time. Now, this is getting, the first part of the talk was on solid ground. Now this is getting speculative, okay? At each step, each slide, it gets a little bit more speculative. So there are lots of challenges to this picture. I'm not gonna, still we wanna talk about what are probabilities in a static picture, if they're conserved, what role does the coherence have to play, and so on. How do we talk about subsystems, because we only have wave function assigning values to entire configurations. And now very quickly, I'm just going to tell you again that many instance idea, the fundamental ontology consists of a timeless configuration space Q. Here I'm thinking of conformal superspace, but this is just because I want to at some point recover GR. I want it to be applicable to a theory like GR. A density function on this configuration space, and the dynamic here is derived from this density, so to speak. And what is this density? There are different ways of arriving at it if you impose certain conditions, like Leonardo did. And in the end, it's kind of lots of mathematical ways to get, if it is a density as a function of the wave function of the width state, or the wave function that you get from the path integral, then I'm going to suppose that there are different ways of arriving at this result here, that it should be given by this norm. And then you compare the volume or the mass of regions A and B, which given this kind of density function. And it's kind of relative counting. Right, so you don't have a problem with recoherence because there's no notion of time, things are just there, but you still can see interference patterns. So I'm going to show you what that is like. Sorry, let me just. Right. So this is a transition amplitude. If you have more than one path, more than one classical path interpolating between an initial configuration and a final configuration. Okay. So very quickly, again, it is a kind of WKB approximation, but you can see here an interference term that depends on the cosine of the difference of the on-shell action between the two classical paths. Okay, and you get this von Vleck determinant that tells you how many paths there are essentially in the vicinity of that path that contribute constructively to interference, and so it gives you more density in that spot. And there are all kinds of interesting relationships here with the Lyapunov experiment, and so on. And so the farther something is away, the less probability, the less paths it will have if the action is chaotic or as a Lyapunov exponent. I'm not going to talk about this that I did. You can also talk about subsystems as conditions on the action when two subsystems decouple. Essentially, you need to look at the second variation of the classical action on the initial points. When you talk about the total field in a region as a composition of two fields in two regions, and you vary just one at a time, you get if that doesn't, well, I can show you later. I don't have time to show you what this is, but it's a condition for the transition amplitude to decouple for 2 points. This is the figure that shows what are the conditions for that to happen. And then we can talk about records. Sorry, now I'm really running. And you can formulate it in different ways that kind of coincide. But the essential feature that I demand of records is that it kind of obeys this Markov property. And you do obtain that if you think in terms of path integrals, and in terms of path integrals for classical paths that are superposing. Here, this point where the two paths have actually crossed. This is a record for this configuration here, a semi-classical record, and you can show that the transition amplitude does factorize for this kind of semi-classical path. So here you can have this low-level notion of interference, semi-classical interference, where classical paths cross and interfere with each other, and the notion of probability is robust for transition amplitudes. Okay, I'm not going to tell you how to extract conservation of probability because I've run over time and I've already talked too much. I'm getting thirsty, and I'm just going to thank you. Let me just give you here. So the idea for the second part of the talk is that there's only a density or volume form in configuration space. And here there's no need to talk about branch counting or any other measure. There's just a single measure. And the density encodes boundary conditions and the quantum dynamics. And the coherence here can just be understood as it's not fundamental to define probabilities. It can just be understood semi-classically as absence of interference among coarse-grained paths, among semi-classical coarse-grained paths. It's very much as in decoherent histories, but it's not necessary. And records, the notion of records, the notion of time, the notion of locality here only emerge semi-classically. I don't have that, it doesn't come in at the ground at the fundamental level. They have to emerge from this kind of path interval. And when there are kind of special subsystems, whose configurations kind of form a clock in the sense that Alex told us about, a physical clock, then you can employ the Page-Woods formalism and extract the conservation of probabilities according to this foliation given by the clock. Right. And then that's the idea is that you have, I'm done, but the idea is that a record of all the outcomes of experiments share the same record. And if they're also related by this kind of, the semi-classical histories have this kind of clock or this kind of special system that serves as a clock, then you can compare the volumes of the different regions of that correspond to the outcome of the experiments that have the same records, and you can just compare their volumes directly because the dependence on the record configuration factors out. Again, I don't really have time to talk about this. So yes, that's it. Thank you.
Hi. So just to clarify, in that slide that you first introduced probabilities that you have that ratio, right?
Mm-hmm.
Of the two mass functions. I think, at least when I look at that, I think there is it is possible to relate that to the approach that Simon Saunders is also trying to do, finite frequentism and so on, right?
You're telling me or asking?
I am asking. Well, I'm telling you that I think, but you agree.
I think so, but I asked Simon that, and he wasn't sure. Okay. So he had some doubts.
But it also seems to me that, for example, in that derivation that I showed yesterday, essentially you get a similar thing, except that here you are focusing on the configuration space.
Yeah. Okay.
And there I impose that normalization condition, which might not always be feasible, whereas here, instead of imposing a sort of universal normalization condition, you have just this ratio. Right?
Yeah, right.
And that might be well defined, as you say, because the ratio might cancel out.
Yeah, right.
But then you say that you want to get probabilities without decoherence necessarily.
Yeah, right.
Well, one thing is that in that derivation of Gojoso that he gets that the Born rule from the assumption of unitary invariance, that I think there is this need to have orthonormal states, and then in the derivation I showed yesterday, the decoherence comes from this condition that you have an approximate orthogonality between the branches. And in the end, that is to justify this mod square.
Right.
And here, how do you justify this mod square measure?
Yeah,
Uh,
okay, good question. And it's complicated. It's not like that. I justify it in a different way. I justified it, well, it's a series of conditions. I can go through them with you.
Okay.
But it requires, it kind of assumes something that it will factorize if you have more than one, if you have multiplications of wave functions, and things like that. And so it's a different set of assumptions. I don't think is as on a rigorous footing as the competitive thing. I think because the justification also at some point I required, I get that I could get anything that is even power of the norm. And then I say something like needs to recover, statistical mechanics or
Okay. But one other question, if you want to define these probabilities for paths that are not necessarily decoherent,
yeah.
but at the same time, the records are defined only semi-classically.
Yes, right.
So do you,
I only get one thing more than the usual idea about decoherence. The only thing I get more than that, so it's still semi-classical, but here my semi-classical paths are allowed to cross. So in the usual consistent histories of decoherence, you don't. Yeah, this is not allowed, but here this is just one little thing on top of that you get. But but it does already accommodate something like a beam splitter. You can think of a beam splitter as paths that reconverge, paths with the same initial configuration that reconverge and things like that too. So basic ideas about recoherence and interference you can kind of recover already semi-classically here. But certain things fail, but which I didn't. That some things you only get in cases where they really decohere. But anyways, I don't know. Yeah.
and maybe if I get one final question. So this idea to define the state by means of this transition amplitude. Transition is not the right word, but
Okay.
so this is to be defined with conformals.
Yeah, the idea here is that these methods, people don't talk about it that much, but there isn't, as far as I know, I mean, you might know this better than me, but as far as I know, the methods of defining probability and so on, for Hartle-Hawking and things like that, they work for mini superspace. And then I wanted to have a way of defining at least, I'm not going to do any calculations with this, I'm going to be honest with you, but at least foundationally, at least conceptually, I wanted to admit the same kind of treatment. That's why I'm using conformal superspace here as a way of getting rid of refoliations.
Right. So this star state it would be in a sense a preferred state from the structure of this conformal superspace.
That's right.
Okay, thank you again.